As images from around the globe flash onto our television screens, it's easy to overlook the technology that brings the pictures to us. At the sharp end of the whole process is the picture tube, the part we all look at. It's our window on the world. To understand how a picture tube is made, we must first grasp the basics of its operation. Electrons are fired at a glass screen, specially coated to glow or phosphoresce. Electrons are very small and fast, but are easily obstructed by gas molecules in the atmosphere. So, to allow the electrons to reach the screen, they must travel in a vacuum. To produce a colour picture, a mixture of three basic colours of phosphors must be present: red, green and blue, arranged very closely together. In a picture tube, each colour phosphor has its own electron source or gun. Each gun is controlled separately, but is synchronized with the other two, allowing each colour to glow at its brightest, be dimmed, or even not to glow at all. In this way, the three colours are mixed to produce all the tones we see in a normal picture. To make sure that the electrons from each gun land only on the right phosphor, a shadow mask is used. This allows a line of sight from the gun to only that corresponding colour phosphor. To build up a picture on a television screen, a focused beam of electrons is aimed at the top left-hand corner of the screen. It's guided along a line at the top of the screen, then it flies back to begin another line just underneath the first one. As the beam travels along the line, the electron guns are controlled to produce the correct colour mixture for that part of the picture. The scanning and fly-back process takes place 625 times to make up one frame of a picture. And there are 25 frames for every second of television viewing. That means the beam has travelled the equivalent of about 4.5 miles for each second in an average-sized television set. The scanning pattern, which directs the beam into each area of the screen, maintaining beam focus all the time, is controlled by the coil, which fits around the cone neck area of the picture tube. That is how a television picture tube works. Now we'll see how they are made at LG.Philips displays, Durham. The key components: flat shadow masks, screens, cones, metal inner cones, rim bands and electron guns arrive at Durham from feeder plants all over Europe and are loaded into the system. Many undergo offline preparation until the appropriate point for them to join the process. The flat shadow masks are annealed to ensure that the mask can be pressed to the correct form or profile without deforming the tiny slots. The flat masks need careful handling, but as formed masks they become even more fragile. Incorrect handling, even picking up a mask by the wrong points, can produce a permanent set, causing the mask to be scrapped. The shadow masks are then blackened by passing them through an oven which contains 1.3% of carbon monoxide, produced by the incomplete combustion of natural gas and air in a combustion chamber. This blackness limits the temperature increase which occurs when electrons hit the mask, causing distortion. It also prevents rust forming when the mask is exposed to wet processes later. So it can be handled and mounted in the screen, a special lightweight diaphragm is assembled. This is produced automatically on equipment known for obvious reasons as a spider. The mask and screen are then matched to produce a unique pair which stay together throughout the rest of the process. A spacing piece fitted between mask and screen ensures that the distance between them is set precisely. Identification in the form of a barcode is attached. Compensating plates on the diaphragm are laser welded to fit the corner pins of the screen. And the skirt of the mask is welded onto the diaphragm. At each stage, inspection is built into the process, and regular measurements are taken to keep the process in control. The mask-screen combinations are then transferred to the next stage by a robot, which ensures that each conveyor position is kept full and also maintains a buffer stock. Up to now, the screen has been a passive receptacle for the shadow mask, but having been matched, it then begins intensive processing. The masks are extracted and washed thoroughly, removing any loose particles. The screen, meanwhile, is also cleaned and treated with hydrofluoric acid to prepare it for the screen coating processes which follow. First of these is the matrix process, the application of extremely fine strips of graphite which will separate the phosphor stripes. This material reduces glare and improves the brightness and contrast of the finished picture. Firstly, a thin layer of photosensitive material is applied to the inner surface. The shadow mask is inserted and the combination is exposed to ultraviolet light, positioned to simulate the position of the electron gun in the finished tube. This hardens the areas on the screen which will eventually be occupied by the phosphors, and the unexposed coating is washed away. This leaves a series of tiny trenches running north and south on the inner surface of the screen, which will be filled with graphite. The layer of graphite is applied to the screen. When it is dried, strong acids etch away the photoresist layer, leaving about 2,000 very thin graphite strips on the screen. Finally, we inspect the graphite layer to ensure that the stripe pattern is correctly positioned, ready for the phosphors to be added in the flow coat room. As in the matrix process, air-conditioned clean room conditions are needed, along with special lighting which does not affect the UV light-sensitive phosphors. Flow coating also echoes the matrix process by making use of the shadow mask to determine the correct position of the phosphors on the screen. The application of the phosphors is done on special mills. First, a thin layer of green phosphor is applied to the inner surface of the screen and dried. With the shadow mask inserted, the combination is placed on a precision ultraviolet light source called a lighthouse. The UV source is critically positioned to simulate only the green electron gun, and this hardens stripes of green phosphor in the relative position. The unexposed phosphor is then washed from the screen and collected for recycling. The process is repeated for blue and red phosphors in turn, with the light source simulating only the corresponding colour electron beam. This order of processing is chosen because red is the most expensive, and with a larger particle size can be easily contaminated if applied before the others. At the end of the flow coat process, under ordinary light, the stripes of phosphor can be seen, outlined by the stripes of matrix. A layer of lacquer is then applied over the top of the phosphors to provide a microscopically smooth surface. Onto that surface, a very thin layer of aluminium is applied to increase picture brightness, to protect the phosphor surface, and to provide electrical continuity. Aluminizing of the screens is achieved by vacuum deposition of a pellet of aluminium. The screen is placed on a vacuum pump, and the air behind the screen is removed. When the correct level of vacuum is reached, the pellet is electrically fired, and the aluminium vapour condenses on the inner surface of the screen. The screen processing is now complete, and after receiving a final inspection, the mask screen combination is delivered to the next stage of assembly. As a multi-product factory, many of our product types are required to undertake differing treatments. One such variation is the bismuth spray. Here our 21 Real Flat and 41 FS receive one further treatment to the shadow mask. A layer of bismuth oxide is applied to the inner surface of the mask to help dissipate the heat which builds up during operation and which would otherwise cause doming of the mask and distortion of the picture. This highly automated procedure involves separating the mask and screen, spraying the mask inner surface with the bismuth oxide coating, and rematching the components. As they will now remain permanently together, the mounting springs on the shadow mask are laser welded onto the corner studs of the screen. The combination now becomes effectively a single component. Now a new component is introduced to the process, the metal inner cone, which is attached to the corner pins. Its function is to shroud the electron beams from the effects of the Earth's magnetic field. As the inner cones arrive pre-blackened, they require only minor processing at Durham, the attachment of mounting plates and the straightening of the edges. The screen is now ready to be attached to a cone, which has been going through its own series of processes to reach this point. The cones arrive in Durham as pressed units, which must first have the neck attached. This procedure involves thermally cracking the stub off the pressed cone to a predetermined length, then gradually heating the jointing surfaces until they are just molten. Once this critical stage is reached, the mill brings the cone and neck together under temperature to fuse the two together. Movement of the molten glass gives a good join of uniform thickness. The joint is then cooled and annealed to relieve any stress built up in the glass. The cones are then carefully inspected and thoroughly washed to remove any surface contamination. To provide an electrical pathway and to reduce the energy of high voltage flashover across the cone surface in the finished tube, a conductive substance called soft flash is applied to the cone's inner surface. The anode connection on the north wall of the cone has a nipple on the inside. This provides the mounting point for a device called a getter, which we'll see later in the process. The neck is carefully cleaned after soft flash application, and the cone is dried. To join the cone and screen glass together, a special jointing paste called frit is used. A precise quantity is measured and carefully positioned in the centre of the sealing edge. The paste, 70% lead oxide, 25% powdered glass, and 5% amyl acetate, quickly air dries into a smooth bead, still fragile at this stage. The cone is now ready to be joined to the screen. The cones arrive, and after having a getter attached, are placed carefully in two special jigs, which locate the cone using the lugs on the cone perimeter. The screen combination can now be placed carefully onto the cone, without dislodging the frit bead. With the components held with their sealing edges in precise alignment, they are fed into a layer which melts and crystallizes the frit, forming a gas-tight seal between the cone and screen. During this process, the lacquer is baked out, along with the other chemicals which were applied during the wet process. The unit is now called a bulb, and is ready for the electron gun to be fitted. First, we must ensure that gases and small particles produced during the baking process are removed. Here the bulb is subject to ultrasonic vibration, as well as bumping, in order to remove the very small particles which could impair quality and create yield loss later in the process. We complete the purging process by flushing the bulb with air to remove the gases and establish ambient conditions inside the bulb. The bulb then travels to the sealing machine, the attachment of the electron gun. The position of the bulb and gun on the sealing machine is critical. All the earlier processes in the matrix area and in flow coat simulated the gun position, so now the gun itself must be fixed exactly in that same position. Once again, location of the bulb is done by means of the cone parabola and screen pads, and the gun itself is loaded onto the sealing pin, which is critically set in the correct orientation to the screen centre. As the sealing mill rotates, the glass of the neck and the foot of the gun are gradually heated until they are almost molten. The culmination of the sealing process is when burners cut in and fuse the neck and foot glass together, with special rollers producing a strong, even seal. The remaining positions cool the glass and, at 450 Celsius, anneal the sealed foot, removing the strain from the neck-foot join. The next process involves drawing all the atmosphere out of the bulb through the thin stem at the base of the gun. The bulbs are loaded onto carts, which consist of a rotary pump, an oil diffusion pump and a water pump for cooling the cart. The carts are conveyed through an enclosed oven called an inline exhaust, which heats the tube to 360 Celsius, expanding the gases inside, aiding their removal. At the end of the ILE, a small sealing oven around the stem is activated, melting the stem glass. As an almost perfect vacuum exists in the tube, the molten glass is sucked into the stem to permanently seal the tube. The remainder of the stem is then cracked off, and the tube travels under vacuum to the reinforcing area. A base cap is fitted to the pins, forming a keyed plug for the electrical connections to the gun. Now for the activation of the getter. To maintain the high vacuum over the lifetime of the tube, a high-frequency induction coil heats the getter, which contains a barium insert. This fires at approximately 1200 Celsius, applying a coating of barium to the inner cone, effectively mopping up any stray gas molecules which come into contact with it. A metal device called a rim band is then fitted around the perimeter of the screen. This not only provides a method for mounting the tube in the set, but it is an important safety device. If the tube should implode, the metal rim band prevents glass from flying around. Firstly, resin-soaked glass cloth is wrapped around the screen. The rim band is then heated, making it expand, and the tube lowered into place. As the rim band cools, it shrinks onto the glass tape. Tubes are then subjected to electrical processing. Connections are made to the pins, and while on the conveyor, the tubes pass through a number of stages. Activating the heaters in the gun prepares the electron-emitting surfaces for operation. Online testing also ensures that the required high vacuum levels are maintained. Passing a high voltage through the components burns off any slight impurities or burrs, electrically cleaning the gun. While in service, the 3 electron beams must converge on the screen with absolute accuracy. This is achieved by correcting the deviations in this convergence by introducing a permanent magnetic field in an Imaco ring situated at the outlet end of the electron gun. Tubes are tested automatically to ensure high quality performance. A dark grey graphite-based coating called DAG is then applied to the outer body of the cone, which, together with the brown internal coating of soft flash applied earlier, allows the tube to be operated as an electrical capacitor. This capacitor smooths the high tension applied to the tube during operation. Without this capacitor, the image on the screen would be seen to jump during operation. Finally, a silicone lacquer is added around the anode by the use of a pad brush. This coating prevents moisture condensing near the anode and therefore stops high voltages short-circuiting to the DAG layer. This coating is cured by the use of UV light. The tube itself is now complete and is given a final thorough physical inspection using green-tinted light to highlight imperfections on the screen surface. Any minor scratches or marks can be polished out using special buffing techniques. After inspection, the various tube models produced by the factory must be separated into streams, as the following procedures vary depending upon type. Before shipping, each tube is fitted with a deflection coil. The coil consists of copper wires, wound in a design which produces complex electromagnetic fields. These fields deflect the electron beam in operation, enabling it to reach the whole of the picture area. During this matching process, each tube is carefully checked for blemishes, which could affect the quality of the television picture once activated. The deflection coil and tube are then permanently secured together using silicone glue to produce the complete picture tube. Finished tubes are loaded into pallets, ready for dispatch to the customer. The high volumes of tubes produced each day require sophisticated handling and packaging techniques, and the process is highly automated. Finally, stacks of finished tubes are loaded into trailers, from here beginning their journey to set-making factories around the world. The process at Durham, from start to finish, takes approximately 14 hours, and the components will have travelled along over 5 miles of conveyors within the factory. There are many critical processes which take place along the way, and in many different technical disciplines. Each of these processes is constantly monitored using statistical process control, SPC, to maximise yields, improve productivity, and provide customers with the highest quality product possible. These controls and repeated product checks maintain LG.Philips' reputation as a world leader in the production of television picture tubes, our window on the world.